Hi, I'm Naoki Kobayashi from the University of Tokyo. In this talk, we'd like to propose a new method for synthesizing logical formulas over integers by using neural networks as gray boxes. Given this kind of learning data, we first train a neural network and then construct a logical formula like this one by using neural network as a hint. One of the applications that we have in mind is to program verification, where we can use this kind of framework to synthesize programming invariant by treating reachable states as positive examples and bad states as negative examples. And another potential application is program synthesis. This is an outline of the rest of this talk. Let me first introduce our NeuGus framework. We consider the following synthesis problem. So as an input, assume that we are given a set of positive examples and negative examples where each instance is a tuple of integers. And the goal is to construct a logical formula phi that is true for all the positive examples and false for all the negative examples. And we use neural networks to solve this problem. So let me explain our idea by using a simple example. So suppose that we are given this kind of two-dimensional data. Okay, this is a visualization of this table data. And suppose that we train a three-layer network with respect to this data, where the activation function is a sigmoid function. Okay, and after training the network, we look at the weights and biases of the trained network, and then try to construct a logical formula by using this weight and biases as a hint. And the idea behind this is that this form of sigmoid function can be viewed as an approximation of a discrete function that corresponds to this inequality relation. So based on that observation, we look at the ratio between weights and biases. And for the first four nodes, the ratio is roughly 2 to 3.9. That means these nodes recognize a half plane defined by this line. And for the rest of four hidden nodes, okay, the ratio is roughly 4 to 1 to 0. That means those nodes recognize a half plane defined by this line. Okay? So based on that, we know that these inequalities are relevant qualifiers. And then we look for a Boolean combination of those qualifiers that characterizes learning data. Okay? So here is an overview of our whole framework. So given the learning data, we first prepare a neural network and train it. But here we actually use 4-layer network instead of the 3-layer network in the previous slide. And the idea here is to let the first hidden nodes to recognize inequalities, and the other two layers recognize a Boolean combination of those inequalities. Okay. And then after training the neural network, we look at the weights and biases of the trained network, and then we extract qualifiers as explained in the previous slide. And then we look for a Boolean combination of those qualifiers that explains the learning data. And to that end, we just need to construct this kind of truth table, where this column shows each instance, and these columns show the values of inequalities for each instance. Okay, and then the problem of constructing phi is just the problem of ordinary Boolean function synthesis from this part of the table. Okay. One point we'd like to stress here is our gray box use of neural networks. We use weight information of neural networks to extract qualifiers. Okay? But we use neural networks only to extract qualifiers, not the whole logical formula. Okay? So that is because directly converting neural networks to formulas would result in too complex formulas. And also, neural networks tend to overfit to the training data and fail to learn the correct formula. And also, by using a classical method in the final phase for formula synthesis, it is easy to take other qualifiers into account. For example, for program invariant synthesis, branching conditions of while loops are often important, so we may wish to add those qualifiers in addition to those found from the neural network. We have implemented our NeuGus method and conducted some experiments. So we have tested our tool to synthesize linear and quadratic formulas of these shapes. So here are some results. So for the synthesis of linear formulas, we have randomly generated formulas of given shape and generated corresponding learning data. And here are some results. So for conjunctive formulas of this shape, our tool could find all the qualifiers that occur in the original formula. And for the nested formulas of this shape, our tool could still find more than 90% of the qualifiers in the original formula. And one point that may need attention is that the three-layer network also achieved good results, contrary to our expectation that three-layer network is not sufficient to recognize formulas of this shape. To analyze the reason why three-layer network also showed good performance, we have prepared this kind of learning data, which corresponds to this simple logical formula. And we have trained a three-layer network. And this figure shows a line recognized by each hidden node after the training. And as you can see here, there are lines that are not related to this logical formula. But if we remove hidden nodes that correspond to these lines, then this network no longer recognizes this learning data. So that means this network does not properly recognize this logical formula, but just does a kind of patchwork to recognize this learning data. So the lesson that we can learn from this is that neural networks do not always learn the correct formula, but even in such cases, the features recognized by hidden nodes can be still useful. So in fact, in this case, although these lines are unrelated, we have still lines close to x equals 0 and y equals 0 that can be used to construct this logical formula. Okay? So that justifies our gray box approach. Let me now explain application of our NeuGus framework to program verification. And to that end, we also need to extend our NeuGus framework. So let me start with some background on program verification. We are here interested in CHC-based program verification, which is a recent popular framework for automated program verification. So given this kind of program, we first construct the corresponding CHC. And here, this predicate sum represents the relation between input and output of this sum function. And these first two clauses corresponds to the definition of sum function, and the last clause corresponds to this assertion. And then the CHC is satisfiable. That means there exists predicate sum that satisfies all these clauses, just if this program is safe. Okay? And in that manner, various program verification problems can be reduced to the CHC solving problem. And we can use CHC solvers as common backend tools for program verification. And here we use our NeuGus framework to improve one of the CHC solvers called HOIS. HOIS is an extension of the ICE-learning framework where the teacher and learner collaborate together to find a model for a given CHC. Okay? So the teacher provides learning data to the learner, and learner uses them to guess a candidate model. And then the teacher checks whether the candidate model is valid or not, and if it is invalid, it provides another learning data, and we repeat this cycle. Okay. So this ICE-learning-based CHC solving turned out to be reasonably efficient, but there was a significant bottleneck in this qualifier discovery phase, which finds basic predicates that constitute a candidate model. So we use our NeuGus framework to improve that part. For the application to CHC solving, we need to generalize the synthesis problem. So the generalized synthesis problem is as follows. So as an input, we are given a set of implication constraints of this form. And this can be considered generalization of positive and negative examples. So we are now given this kind of learning data. Okay? And then we try to construct an assignment of predicates to each predicate variable so that all the constraints are satisfied. So to that end, we extend our NeuGus method. So given the learning data, as before, we prepare a neural network and train them. But since we now have multiple unknown predicates, we prepare a neural network for each predicate and train them together with this kind of loss function. So this loss function is designed so that the constraint is satisfied if and only if the loss function is 0. Okay? And otherwise, the value of the loss function is positive. And then after training the network, we can perform qualifier extraction as before and proceed to the formula synthesis. Okay? And now slight extension is necessary here as well. So we basically perform Boolean function synthesis in a classical manner. But the problem here is that target labels for some data cannot be decided from the input data. Okay? So for those data, we trust the output of neural networks and use that for the formula synthesis. Okay? So once we trust the output, then the problem of formula synthesis is just an ordinary Boolean function synthesis problem. Okay? And then we can find formula phi. That's it. We have implemented the extended NeuGus method. So we have extended Hoist with our NeuGus framework so that given a CHC problem, we first run Hoist, but periodically invoke NeuGus to find appropriate qualifiers. And we repeat this cycle until Hoist succeeds to prove or disprove the satisfiability of the given CHC. We have conducted some preliminary experiments, and this benchmark set is rather small, but all the instances are those of which plain Hoist timed out. And another CHC solver, spacer, also times out for some of these instances. But our new Hoist, extended with NeuGus framework, could successfully solve them. Okay, so now let me briefly discuss related work. Most closely related to ours is a work on CLN2INV, where neural network-based logical regression has been used for program invariant synthesis. Our NeuGus framework works in a more general learning setting. There are other approaches to use neural networks for program synthesis. For example, Zhu et al. Has proposed a black box-based approach. There are also other data-driven approaches to CHC solving. For example, Zhu et al. Used SVM. And we believe that our use of neural networks are suitable for synthesizing more complex formulas. We have proposed NeuGus framework, which uses neural networks as gray boxes to synthesize logical formulas, and applied it to program verification. Future work includes a synthesis of more complex program expressions and improvement of scalability and precision. Thank you for your attention.